Reloading podcast here on the Firearms Radio Network, presented by Patriot Patch Company and Camerado. Let me fix that. So tonight we have a guest who has been nice enough to join us, and also he'll be taking questions in a little while. We do have a presentation first that we're going to go through, but we have Jeff Seward from Bulletology. And then we've got the usual cast of characters. Jeff, what we like to do is kind of start off the show by talking about, what you've done in reloading and shooting and stuff this week, except for Nick just bailed. But the rest of us can talk about it.
Sure. Sure. Well, I'm sort of semi-retired ballistics engineer. I'm still doing work on things that that I enjoy and that excite me. I'm 2024 recipient of National Defense Industrial Association's Chin Award. And you go on the NDIA website and look at that, and you can see that they don't give those away to everybody. So I'm very honored to have received that. I'm the author of a book, Ammunition Demystified. It's available on Barnes and Noble and Amazon, and basically it condenses my 40-year career into about 450 pages of information. So if that's something that after listening to me tonight, you decide it might be more information that you'd like to have, feel free to go ahead and pick one of those up. Been reloading since 1983. I just looked at my records, loaded in the neighborhood of 10,000 rounds over the years. It's not a big pile, but loaded everything from, 17 Fireball up to, does 50 caliber count?
Yes.
Oh, yeah. Okay. Well, that was for work, but okay. There you go.
That was for work.
Yeah, and bigger things from that, but yeah. So over 40 years, I worked on tank ammunition, artillery ammunition, medium cal, small cal. Worked on a pile of different things. Worked on fuses. Worked on rockets.
Oh wow!
Yeah, a lot of different topics. So. I freely admit I don't know everything, but if I don't know, you'll know.
Well,
that's with a lot of fun stuff.
Yeah, sounds like a fun job. Get to watch stuff go boom.
You know what? I look back on it and I realized I was very blessed to have kind of fallen into that. It's one of those deals where, I graduated college in 77, spent a year and a half in Saudi Arabia, got back from there. I started looking around for a job, and I was at GE in Burlington, Vermont. And what popped up was this job in the ammo group. And I'm like, well, I'll do this until it's not fun anymore. And it never stopped being fun. So, ended up spending 45 years doing this. So.
That's the best part, when it stays fun for all that time. And even as you're semi-retired, you're still doing it. So
right. I'm doing some work on some rifle barrels at the current moment for a company in the Midwest. Doing some other design work.
Are they in Wisconsin by chance?
Unfortunately, no.
Because we have like 4 barrel companies in Wisconsin.
5.
Right.
Oh,
so,
sorry, 5.
Kind of what I'm after. What I'm after is a thing known as gain twist, where the rifling angle changes as you go along the barrel.
That's me.
And so I guess I'd like to hear at some point your experiences with gain twist, because mine comes from kind of a medium cal perspective, where it's kind of a must-have for those guns.
Yeah.
Well, I have the original Game Twist rifling, Paul.
Yes, you do. You
So-
do. But I'm a more modern game twist person, so yeah. I'm also a left-hand twist person at the same time.
Oh, one of those guys.
Yeah.
Fighting Coriolis, are we?
Fighting it all, for a right-handed person, a left-handed twist works best. Just the way when the gun recoils, the bullet engages the rifling, the the way the gun wants to recoil to the left or to the right, depending upon your twist rate as the bullet engages. Yeah, there's lots of advantages depending upon left or right-handed, and the game twist. I find that if it didn't take so long to get a barrel done by a barrel maker for game twist, most of my rifles would have game twist in them. I find that it was a year and a half to get 2 barrels made. So
Sounds pretty painful.
yeah, but accurate, extremely.
Okay, that's good news.
Yeah.
I would like to pick over your data at some point if you're agreeable to sharing that information.
Sure. It's a Bartland barrel, so you want to know, and I started out at a 14 twist and ended up at a 12. It shoots 85 grain Sierra 1530 bullets in call it the twos, okay, just to be honest. And I am not the best shot anymore. My sight and steadiness are slowly going, but in the right hands, the gun will shoot in the twos without a problem.
That's very respectable.
And
I don't have anything that'll do anything close to that. So, right, Mike, do you want to start with the presentation?
Let everybody else kind of say hi and
No worries.
Okay,
Sure.
and then we'll go into it. Jim, what you been up to?
Unmuting myself.
It can be a challenge.
Anyway, no, I've been busy making bullets, usually over the weekend, but I've been making some 40s, some 9s, 338s. It's interesting. I've got about 2,038 caliber bullets to do a lot of development testing on. Unfortunately, the caliber I think I have 2 calibers in that diameter. My 35 Remington barrel and my 357 barrel for my contender. That would be an interesting comparison. 35 Remington, compare that to 357 Magnum.
Nice.
Mm-hmm.
But
Ray,
anyway,
how about you?
Just been moving everything. Kind of decided I have way too many bullets and loaded ammo and powder and lead, and it really makes bad. I got to lug it all up out of a basement. So
That's terrible. I'll come down and rescue some of that from you since you said you have too much.
It's all at my house already, so you got to
Not
come to
everything.
my house.
Oh, well, if it's at your house, then he doesn't have
Most
much
of it
anymore.
is. Most of it is.
I still
I
got a
would
lot
say.
of bullets and stuff here. So and
So
brass.
then he doesn't have too much anymore.
No.
Because you have it all.
He gave it to me.
There you go.
Yeah.
See, he
He
solved
gave
the
me-
problem.
He gave me 1,000 pounds of ammo or something, whatever that was.
Now he
One
doesn't have enough.
I still got enough to get by here, but
There
that's
you
what
go.
I've been just packing up, moving, painting, stuff like that.
Yeah,
Getting ready to head for freedom.
there you go. Ray's following his son's lead and escaping from Illinois. So
that's all to new with me.
I loaded up some 9. That's about all I've done. So, but I haven't really bothered to try and adjust the primer on the Square Deal B. It keeps popping like it was during the demonstration. So I should probably get serious about that. It's not a problem unless there's no case there. Then it launches a primer across the room.
Ooh,
Kind of like
okay.
a D10 spring. So. Alrighty, so we're gonna share this, and then we're gonna go over here. And why is it? Yeah, let's try this again. That's not the one I want. I want that. Why?
Should just hit your space bar.
Oh, that's all fun. Ooh. Wow, that's scary.
Yeah.
Let's try this again and see if it'll actually let me do it this time. It worked before when I did it in test, so sorry. No, we don't want that. So are you seeing that you are currently sharing your screen, or are you seeing the images for Reloader Podcast?
Images for Reloader Podcast.
Okay, good. All right, so it's working now. Just fine. Jeff, the only thing is it had a problem with the graphic you had in the upper right.
Oh, all right, no worries. We'll survive without, no problem.
So
All right, so you want
otherwise-
to go to the next slide over? Uh-oh.
Oh, well,
Well, this is going to be a pretty boring presentation if we don't have images.
for crying out loud. Did it not? So it only showed the first one.
No, I haven't. There's no photographs displayed.
What the heck?
It was saying something about repaired. That file.
Well, somebody in the comments has asked about zinc bullets.
Yes, that's
Yeah.
handy.
Yeah. So once upon a time, this is going to be, yikes, 15 years ago now, I did work on zinc bullets as a non-toxic alternative for a rim fire manufacturer in the U.S. And I thought they had a lot of promise. There were things that needed to be done, like some sort of protective coating, like the bake-on stuff that some of the guys use, in order to shield that from putting zinc onto the interior of the barrel. And we needed to kind of take it a little bit farther, get nonlinear material properties and run it through some finite element analysis to understand how the material was going to behave. We didn't get that far, but I thought it had great potential for non-toxic bullets.
Okay, so so with a powder coat finish that would go on it in order to keep the zinc from affecting the barrel, and it would you had a very promising
Right. And down below, somebody wants to know if this is the guy that was on the Hornady podcast. The answer is yes. Yeah, that's been a long time now. Like I said, it's 10 years anyway, might be 15. And yeah, the interesting part of that was we got to look at the behavior of lead bullets, kind of the gold standard for rimfire 22, and compare it to the zinc. And the zinc, I thought, was not an identical match because the density is not quite as high as it is with lead, but I thought it had a lot of potential.
Were you using the same size bullets? In other words, the physical size?
In terms of the diameter, the answer is yes.
Okay.
The other details, I'm kind of drawing a blank on at the moment.
Because I wondered if it was a longer bullet in order to gain weight, or
Yeah.
you know,
So the real problem is you don't have a lot of gyroscopic stability margin with the
okay.
length of diameter that you currently have with a lead bullet. And when you go lighter, you lose polar moment of inertia rapidly. So you might actually have to go shorter L over D to keep the thing gyroscopically stable.
Okay.
So it was one of those you're in because of the twist of all the legacy 22 rimfire rifles and handguns out there. You're really in a bit of a corner with regard to keeping the bullet gyroscopically stable at launch.
Okay. So, yeah, so you had to keep with a short bullet in order to be stable, and or the same size.
Yep.
But it was so light that it affects your you don't have enough mass there to really maintain accuracy at longer range.
Yeah, you're really, yeah, and to be honest with you, anything that you do with an alternate material that's lighter than lead, you're going to be hard pressed to match the performance of lead. my opinion.
Mm-hmm.
I mean, lead's a good material for bullets for a lot of reasons. You know, the very high density, the low yield strength, the wonderful elongation and failure. Those are all kind of really tough to replicate in alternate materials.
Yeah, being a malleable material, it functions very well with in a number of different configurations, either coated, jacketed, or just
Yeah.
plain. Yeah.
And somebody mentioned that they've been shooting zinc bullets for 5 years, no powder coat, no issues with zinc fouling. I if you're using them for a pistol application where the velocities and pressures are low, I could see where you could get away with that. If you're trying to drive them to rifle velocities, things might not behave as benignly as they do in pistol application. Yeah, Andy said something about 30-06, 180 grain lead, 113 grain zinc, and I don't know any more about that. So,
Well, he casted some bullets that were 180 grain lead, and then they came out to 113 zinc.
okay.
And he's getting out of 30-06, 3,200 feet per second.
That's cooking along pretty good. And
Yeah.
I would be looking for deposits on the driving side of the lands in the barrel to see if you've left anything behind. And I mean, basically, the wear of the driving surface of the bullet is related to its melt temperature. So copper has a melt temperature around 1900 degrees Fahrenheit. Lead is considerably lower, like 600 if memory serves correctly. Zinc is a little bit higher than that, if I'm remembering correctly.
Yeah.
So, like, perhaps a little more velocity than lead, you might be able to get away with it.
But 3,200 feet per second would be rough.
That I would expect to leave a fair amount of residual material behind in the barrel.
Now, have you ever experimented with like HBN2 or anything like that in coated bullets to keep the fouling down?
You're going to have to fill me in on what that is.
HBN2 is um, oh, it's a boride coating. It's like Molly, but has a higher melt temperature. In other words, it's in the 36 to 3,800 degrees before it melts.
Okay.
Where Molly is a much lower temperature.
Yeah, I don't have any firsthand information other than back in the early 2000 time frame. We were doing some push testing for the U.S. government on small cal bullets, and we took cut up barrel sections and pushed both 5.56 and 7.62 bullets through some barrel sections and measured the push force as a function of travel, so we could kind of update and integrate that information into the interior ballistics models.
Okay.
So one of the things that we found was once upon a time, Barnes offered for sale a bullet they called the XLC, and it had a dry film lube on it. And the resistance, the inboard resistance of those bullets was kind of a pretty tiny fraction of what it was for the regular X bullet. Back before they had the triple shock.
Right.
And I mean, it was like 20% of what the X bullet was. It was kind of shocking how big the difference was.
Yeah, it's HPN2 is hexagonal boride nitrate, and it's used in the main use in the United States is used in um, uh, women's foundation and stuff like that.
Oh,
But
okay.
the steel industry uses it to lubricate the hinges on their blast doors and stuff like that because of the temperature that it melts at, and it works as a fine powder lubricant.
And I think if you were to use that kind of as a physical vapor deposition on the OD of the bullet, it'd probably work just fine.
I use it a lot in my prairie dog shooting rifles because they seem to.
And how do you apply that?
I apply it by impact method, so I add my bullets into a vibratory tumbler or a rotary tumbler, depending upon the size that I need to deal with.
Okay.
And there are steel BBs in there that have been coated in the HBN2, and I measure a small amount of HBN2 depending upon how many bullets, and let it run for 10, 12 hours. So they're kind of impact plated is how I would call it. Have to start out with extremely clean bullets. I usually use either acetone or denatured alcohol to clean all the bullets first, no grease whatsoever on them, and then move them into a vibratory or rotary tumbler and let the steel BBs then impact the bullets, and it's transferred that way.
Okay.
All right, Jeff, we've got it up.
All right. Have we got images?
Yep.
Okay, cool.
Oops, I didn't want to click on that to do that. So now we're on to the second slide.
I'm not seeing any photographs of the cartridge cases here.
It says repaired, so I'm wondering if there's some of it missing.
I opened it, Mike. I think it was something. He has a virus scanner thing. I'm wondering if when he emailed it to you, it removed all the images.
Oh yeah, because it says pictures cannot be displayed.
Yeah, pictures can't be displayed. And there's what does it say? AVG or something like that, or AVI, which I know is a virus.
The AVIs I sent separately.
Oh,
The rest of them, I think, were JPEGs.
weird.
You can't see me either, Nick?
I'm getting the same thing as Mike. It says pictures can't be displayed.
Can Jeff run it on his end?
Should be able to.
I'd be happy to. What have I got to do over here? Just drag it over and share the screen?
If you go down to you should have an option to share screen. I think I don't know, use your guys' screen a little different than mine. I've got mute, stop video, add cam, share.
Yeah, so
react.
right next to the X circle, there should be a share button.
On the bottom of your screen.
Yep.
All right. Yep.
Yep.
Okay, screen one. There we go. All right, so I have ripped the AVIs out of this presentation. So you're going to have to spot for me, Mike. Okay.
Mm-hmm.
All right, let's move on. All right, so Mike and I batted around some ideas about the topics here, and so this is what we put together, and it talks pretty heavily about cartridge cases and some of the things you might run into. There's also a few things on why high ballistic coefficients are attractive, yada yada yada, and a few other topics that folks might find interesting. Okay, so the first slide here, we're talking about case material options.
We're not seeing the slide.
I think, Mike, you have to bring it up.
It's not in there.
It's not in there, huh?
It's not in there to bring up.
Well, rats and fratson.
Did Jeff share his screen though?
I did. Oh, hang on. Share. Let's try that. Please upload your presentation. I don't want to be. No. Okay. So if I go right now, I'm okay. Let's try this. Allow. Can you see my screen now?
You hit the right window. It'll say window. There you go.
There we go.
That's it.
How about this?
Yep.
Full screen. We got images.
Yep.
Okay. All right. Let's move on here. Yeah. So we've got brass, standby. There are steel cartridge cases. That one happens to be a Russian 545 by 39, and got a lacquer coating on it for corrosion protection. We've got an aluminum handgun cartridge, and those, aluminum is kind of the material of the future, right? Well, it was first introduced commercially, well, not commercially, in military sense, in the early 70s with the development of the GAU-8 cartridge on the A-10 aircraft. So aluminum has been around as a cartridge case material for a long time. Okay. Next one over is a combination brass plastic cartridge case. After that is a steel plastic that was made by True Velocity. And then the last one on the far right-hand side is made by Shell Shock, and it's an aluminum base with a corrosion protection coating on it, with a drawn steel cup that's kind of crimped in the primer pocket. So it's a really interesting approach to solving the let's save some weight necessity for the military. Okay. And for better or for worse, some of these, notably the steel and the plastic offerings and the aluminum steel offerings, you're going to get higher bolt loads as a result of the cartridge case not being able to share as much load in friction between the case wall and the interior wall of the chamber. So as the case is pressurized, there's a fair amount of load that can get dumped out in friction through that case wall, the body of the case wall, that interface. So the real problem for us reloaders and shooters is the fact that the gun life decreases pretty rapidly with case chamber friction. And the next slide is a video, and we'll have to come back to that one. But basically, it's an animation of the cartridge case expanding out to contact the chamber. And Mike, I think we'll have to come back to that. I don't want to interrupt while we're doing this.
Okay.
Okay. And basically the case mashes out to hit the wall. You can see, you'll see exactly where the case hits the wall, and then the composite structure of case and chamber deflects outward to seal the bore, and then it contracts, and at the end of the interior ballistic cycle, that you'll see the case wall shrink to fall out of contact with the case wall. So it's a pretty interesting animation. Okay, so this slide is a slide that shows the relative bolt load for 4 different cartridge cases. The yellow diagonal line is 5.56 with a brass case. The gray line is an aluminum case. The blue line is a steel case. And way up at the top under the red dashed line is a polymer case with a polymer body with a brass base on it. Okay. And so you've got lines on there for wet or lubricated cartridge case. And so anytime you lubricate it, your bolt loads are gonna go up. That's just the fact of life. Okay. You've got a vertical line for dry, and that would be, you've inserted the cartridge case into the chamber. It's completely free of any fluids, lubricants, water, etc. And then over on the far right-hand side is a dirty cartridge case. So this would be a cartridge case that's contaminated with some sort of high friction dust or dirt, something like that. And so it just gives you an idea how the different cartridge cases behave. And so from a gun design standpoint, what the gun designers use is just the pressure times the area acting on the base of the interior of the cartridge case. And that polymer case, you can see you don't get a whole lot of relief as a result of having that. So for this exercise, this assessment, I held the peak pressure at 52.5 thousand PSI. The cases are all designed to have a percent of ultimate strain less than 100%. In other words, when you're done with the firing cycle, the cartridge case remains in one piece. Okay, and so then we want to go look at what happens to the relative peak bolt load as a result of these different case materials. All right, and so over on the right-hand side is a graph that shows the relative fatigue life of your gun for a dirty case, which is just under 1.2. Between those two, the purple and the dark blue line, there's a dry case in there, just about 1.25, and then way over on the right-hand side is a red line, the lubricated case. So when you increase the bolt load, you lose fatigue life somewhere between the square and the cube of the increased load. So if you increase the load by 50%, it'd be 1.5. Your parts life would be somewhere between 45% and 30% of the baseline load. Is that a lot? Yeah, it's a lot. But if you were to, for instance, lubricate your cartridge cases to do the resizing job and not clean that lubricant off, you're going to double the boat load. So you're way over at 2.0. Okay. And that's taken from medium caliber firing data where the bolts were instrumented, and so we knew how much the lubricant increased the load. Doesn't end well. So kind of a word to the wise, a takeaway, it would be if you're resizing your cartridge case with some sort of lubricant, and everybody does, do your best to clean off that lubricant as thoroughly as you can. Okay, because you'd much rather throw away a cartridge case than throw away a bolt on a gun. Okay, and pardon me, I've got a cat pestering me. That's cats that's been fed. Okay, any questions here? All right. And I'm going to see if I can find some way to see them. All right. Okay, I'm not seeing any questions on the.
Nope, no questions yet.
Okay.
If there's any questions, it'll pop up. I'll pop it up like that.
All right. Okay, so the next slide here, general cartridge case design guidelines, and this is for brass. Okay, so things that have to happen. First is a tapered case body, and that makes the extraction easier. And kind of the steeper the taper, the easier that becomes. So it's a matter of what's the press fit when you're done firing, and how far do you have to move the case aft till the press fit's removed. Okay. So if you look at the new cartridge cases, like 6.5 Creedmoor or the PRCs, those case tapers are pretty shallow compared to military cartridge cases. And that, since we're not putting them in a machine gun, kind of no harm, no foul. But if you're going to put that in a machine gun and operate in, let's just say, less than ideal cleanliness conditions, you might be disappointed with the performance of those cases. Okay, so the next item is tapered wall thickness, and cases are always thinnest at the mouth, thickest at the aft end. And the reason for that is you want the case to seal at the mouth first so that you don't get any gas leakage past the cartridge case. And you don't get any gas residue that gets deposited on the case aft of the neck. Okay. And then the next item is gradually tapered material properties that ensures each portion of the case can do its job correctly. You have stronger but lower elongation and failure at the aft end, basically the extractor groove area, and then softer but more ductile near the case mouth. So when you go to resize them, kind of where all the work's done is up near the shoulder, and the case neck, and so that's where you really got to apply the lubricant when you go to resize. Okay. Headspace control is dictated by gun needs, sealing, feeding, that sort of thing. So that's kind of on the gun designer. And then lastly, the design margins are determined by the percent of ultimate strain, not by stress. So almost all of these cartridge cases, if you're operating in pressures above kind of even modest pistol, so if you're operating above, say, 20,000 psi, the case is going to stretch some, and it's not going to come back to its original dimensions. So that case has, engineers would call it yielded. So you've pushed the stresses above the yield point, and so as a result, most engineering things, you look at what's the factor of safety. Well, cartridge cases factor of safety is not a valid design criteria. It's really percent of ultimate strain, and ultimate strain is really just okay, if you stretch this material until it fails, what percent of that does each of the sections of the cartridge case see? Okay, and so for a typical, like say 5.56, I worked with 5.56 a fair amount over the years. A typical worst case percent of ultimate strain might be only about 60 or 65% of ultimate. So there's usually a fair amount of margin just because of the reliability requirements that are placed on the ammunition. Okay, so here's a slide that shows the forming steps for a brass cartridge case. You start off on the left-hand side with a cup, and then you do the first draw, you do the second draw, and then you pre-form the primer pocket. The next step, you draw a little more, and you do another pre-form on the primer pocket. The third, the fifth step there, you put the extractor groove in, and then moving further to the right, you put in the shoulder. You basically preform the shoulder, and then the second to the last step, you'll notice that case has been annealed, and because you're putting so much work into it, that's going to need to happen during the forming process. And on the last step here, it shows that the flash hole has been punched. Okay, and each manufacturer has their own series of steps that they perform in order to make a cartridge case, and they're optimized for their factory. Shall we move on?
Absolutely.
Okay.
Sorry, I had a cough, so I was muting.
All right. So from an analytical standpoint, the analyzing what's going on in a cartridge case is pretty complicated because there are three different stresses or strains present in the cartridge case along the body. So there's a strain, or actually stress and stretch in the axial direction along the longitudinal axis of the cartridge case. There's a radial strain pushing in from the out from the inside, due to the internal pressure, and then that causes a hoop strain to develop. So you've got stresses in three different directions at every section along the length of the cartridge case. Okay, so from an analytical standpoint, you have to, any analysis you do on them has to take into account those three stress and strain conditions. Okay. Now, in terms of stretching, where does the case stretch most? Well, usually it's just aft of where the case body last contacts the chamber. And if you do it enough, you fire it enough times, you're going to stretch it and thin it, as shown with the big red arrow on the right hand side, and you can get separations there if you're not paying attention. And a lot of guys use a paper clip test to find this stretching. I have used that test, and I have been successful in finding stretching. You need to be diligent about it, particularly with rifles, and I would say also particularly with cartridges with a belt. Questions at all?
Doesn't seem to be any yet.
Okay. So we'll go on to the next slide. All right. So here are the different types of head spacing schemes that are used. In the upper left is the shoulder headspace, and most people pick that these days if they're doing rifle cartridges. Okay, down below there on the left is a belt headspace, and basically there's a big, larger diameter boss that stops the cartridge case from being seated any more deeply into the chamber. Okay, on the upper right-hand side is a rim, and that's typically used with revolvers or shotguns. And then down at the bottom on the right-hand side is a case mouth headspace. And basically you've got a stop in the chamber that the cartridge case mouth fetches up on to limit how deeply the cartridge case can go into the chamber. Okay, and so the headspace selection is really, in most cases, driven by the considerations from the gun design itself. I mean, how am I going to handle this thing? How am I going to feed it? Where do I stop it? Is there an extractor? Does the extractor limit the travel? Blah blah blah. So there's gun considerations that have to go into how we choose to headspace the cartridge. Okay, and then the next question you have to ask yourself is there a spring, like from a spring-loaded eject plunger, that pushes the case forward in the chamber? So for guns like the old Mausers, there's no spring to push that forward. The Remingtons, the Savages, those bolts have a spring-loaded plunger, and they're going to push the cartridge more deeply into the chamber and open up so that the case will be in intimate contact up on the shoulder or on the belt, and if there's a gap in the system, there'll be a gap at the base of the cartridge case. Okay, I'm currently reloading some 300 Win Mag for my nephew, and we had a bit of a go round the last time I did that. Basically, I loaded up 20 cartridges on a 300 Win Mag, and used my standard reloading procedure, sizing procedure, and tried them, and they wouldn't fit in the gun because the shoulder was too long. So in my opinion, it's kind of goofy to have two things that can control the headspace when really what you would like to have is one. All right. Questions here?
Geez. I've been an advocate of with Magnum cases of head spacing off the shoulder with 7mm Remington Magnum 300 Win Mag
Yeah.
is to work at pushing the shoulder back and not worrying about the belt.
Yeah, and it's really a bit of a balancing act, trying to have the shoulder bumped enough so that the rim doesn't fetch up first.
I have found that the belts are usually shorter than where the shoulder will be after after the brass has had one firing on it, or maybe two, depending upon the
Yeah.
chamber of the gun.
Yeah. So with my nephew has a Browning X bolt, and like I said, I loaded what I thought was typical, and stopped hard in the gun, and I had to pull all those bullets, go back through and resize, basically bump the shoulder more in order to allow them to chamber. And my experience has been the shoulder headspace is kind of all over the map with those guns. I've found, just the ones that I've looked at here recently, I found as much as 10 or 12 thousandths difference in that headspace dimension.
Exactly. Yes. Off the shoulder, working off the shoulder.
Right.
There are a couple cartridge companies that are making longer
Short?
brass, so that you
With
can
with
actually
with
push
shorter heads with the shorter
Right.
headspaces.
No, they haven't adjusted that. They're making a longer piece of brass
Okay.
that you can push the shoulder back, so you can get your 2000s off of factory case now.
Okay.
I never had any issues with that with my buddy's 257 Weatherby, but it was a Mark V, so chamber is going to be, probably a little more precise than a lot of your
Yep.
off the rack rifles.
Right. 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 Shall we go on?
Absolutely.
Oops. All right. Stress corrosion cracking. So stress corrosion cracking is something that happens from time to time in brass cartridge cases. And stress corrosion cracking is caused by basically three factors have to be present. The first is the material has to be susceptible to it, and brass is susceptible. Okay. The second thing you have to have is a corrosive atmosphere, and for brass, high nitrogen content is corrosive. And then the last thing you have to have is a residual stress pattern in the material. So typically what happens is the case looks just fine when you load it in, but internally what's happened is there's a crack that has gone partway into the case wall, and then that crack moving into the case wall relieves some of the residual stress, and the split no longer runs. It doesn't progress any more deeply into the cartridge case wall. And so everything is happiness until you fire it. And then what happens when you fire it is that split pops the rest of the way through the wall, and you're left with kind of what you see there in the image. Okay. And it happens with center fire, it happens with rim fire. The next slide shows 17 HMR with varying degrees of stress corrosion cracking. Okay. And I think the problem with the 17 HMR was related to the fact that they probably primed them prior to, putting the shoulder and the neck in at smaller diameter. So it's just easier to get the blob of primer material down into the case with the prior to putting the neck in. And then once you spin the primer into the rim, you don't want to do any more stress relieving because that'd be a silly thing to do. So they didn't do it. And at least early samples of 17 HMR suffered from varying degrees of stress corrosion cracking in the shoulder. And you see a longitudinal split like that, what's caused it is stress corrosion cracking.
Yeah, see, on reloads, sometimes we think that's a lube dent that's split, but it's nice to know that that's not the case.
Yeah, so for a lube dent to cause that, it would have to be kind of fatigue related. And so if you've got lots of firings on them and you bump the hardness up and you haven't annealed, then you have the potential, obviously, to cause that. But my experience is that they're almost always, excuse me, caused by stress corrosion cracking.
So people don't need to anneal as much as they do?
No, I'm not suggesting that. I'm suggesting that when they see that it's caused by stress corrosion cracking, my experience is this rarely, unless the leak progresses to the point where the leak path extends aft out of the gun, towards the bolt, there's no problem. There's no harm to the firearm. Just throw the case away. And if you're starting to see it on reloads, you might think about annealing the case. Okay. So for these,
Here's a question for you.
sure.
Clifford Zach wants to know, does annealing increase corrosion?
Does it increase susceptibility to corrosion? The answer is no, quite the opposite. Is the case more corroded during the annealing process? I don't think so. Okay. And does this affect dispersion? I don't have any. It's not that I don't have any firsthand experience with this. Obviously, I do. Otherwise, how would I have taken the pictures? But I didn't notice a radical flyer as a result of this.
Yeah. Raggle Fraggle wants to know, do you find the stress is different from rimfire versus boxer prime cartridges? He thinks it would be different due to the flash hole.
The residual forming stresses are definitely different. You have to have, because you have to resist much higher pressures in a boxer or Berdan prime case. The material down near the primer pocket has to be kind of extraordinarily strong. So, but that doesn't answer the is there residual stress in there question. Let's just say that it's not annealed. Okay.
Okay.
And any more questions?
Not currently.
Okay. So here's another nasty thing that people sometimes run into. It's a thing called verdigris. And it's a toxic green corrosion on the exterior of the cartridge case caused by contact with tanned leather. Typically, it's tanned leather. Okay, the stuff is toxic, can cause gun malfunctions, case separations, and it's really the reason why you can call it safari ammunition and police ammunition for revolvers is CAD plated. Okay, so can you clean it up? The answer is yes. You just got to be careful that what you're taking off is dealt with appropriately because it is toxic.
Can you explain CAD plated?
Cadmium.
Okay.
Cadmium, or are they using something else? They're using something else these days, and I'm drawing a blank on what it is. I'm sorry, I don't.
We call it nickel plating.
Yep, and I'm sorry, that is more likely to be the case. Yes, nickel.
Yeah. Yeah, the cadmium they've gotten away from because of the carcinogens in it. Yeah.
Yeah, heavy metal. Yeah, nickel's not real good for you either, but yeah, it's better than cadmium.
This is actually physically a loss of area of the case.
I'm sorry, what's that?
You're actually losing area of the case here when you get this green corrosion.
Yeah.
Which would reduce your wall thickness.
Yes, it can. Yep. And that would help explain the case separations as a result of this.
Correct.
Okay, and if we got no questions here, we'll move on. Okay, so this is another case failure type that I saw this has happened to be Lake City 30-06 brass that I had converted to 25-06 back when I didn't have two nickels to rub together. And basically, I had 3 reloads on this brass, and I found this rather peculiar failure mode at the very base of the cartridge case. And, I started thinking about this a little bit, and it's my belief that this is caused by excessive work hardening from multiple firing and resizing cycles. Okay. And the real problem with this is the old paper clip test won't find it. The crack is so tiny and so insignificant that getting in there with a paper clip, you're not going to be able to find it.
Okay.
So the deal with brass is you're always trading off yield strength for elongation. So back at the extractor lip and primer pocket, you want really high yield strength, and the penalty you pay for that is very low elongation and failure. Say only 2 or 3% perhaps, maybe 4 if you're lucky. Okay, so that's really the trade-off that you make when you're building cartridge cases from brass.
Okay. Now, I use the case head to measure pressures. So if I measure my cases and I'm getting a thousandths growth in the case head, that's
let me ask you a question.
Sure.
Why are you using case head? You're using case head diameter, I assume.
Yes. Uh-huh.
Why would you use case head diameter and not headspace dimension?
Headspace dimensions, I find in at least in my guns that it doesn't move any more than after I shoot it. It's right there. But if
So I would tell you, if the pressure is high, you've got likely more bolt to bolt movement as a result of that, and so you ought to expect to see higher headspace dimension compared to a lower pressure cartridge? I'm just asking.
I'm looking at, cartridges that are in the 60, 63, 64,000 PSI range.
Yep.
And I have found that if I see a 1,000th growth in my case head, that's if you look just above where your crack is, just to the left,
Yep.
measured across there, that with a very accurate micrometer, if I find that, I'm over pressure.
So you're measuring before firing
right?
and after.
Yes.
Okay.
Yes. Because any growth in that area tells me that I've exceeded. I don't believe in looking at primers anymore because primers lie.
Primers lie. That's a good line. I mean, there's a lot of problems with primers, and I guess we can kick it around a little bit. But I mean, just things like, what are the dimensions of the primer versus the pocket? What's the roughness of the pocket? What's the headspace look like on the gun? So when you set the primer off, the first thing that happens is that primer cup comes slamming back to the bolt face.
Yep.
Okay. And then the hot particle filled gases go venting into the primer bed, or the propellant bed, and then things start taking off. And once the bullet leaves the cartridge case, then the case can slide back. And so, depending on the details of how the primer cup grips the cartridge case pocket, you can have signs of quote unquote pressure signs on the primer cup that may or may not be real.
Right. And the other thing, if you have a spring-loaded ejector, that you look for ejector swipe. So, or a hole where, or a mark where I won't call it swipe, but it'll be a circle on your brass case.
Yep. Yep. Seen those enough times.
Yep. So, going back a long ways, Vernon Spear was the one that taught the gunsmith that I was taught by to look at the case head expansion, and if you got a 1,000th growth and expansion on there, you've gone past your limit on the case.
Okay.
So.
All right. Any more questions here? Okay, let's move on. So, if you happen to come across a cartridge case with these little dimples up near the base of the shoulder, these are signatures on the cartridge case from what's called a conformal pressure transducer. And these cartridges were fired in a test fixture specifically to measure pressure. So, if you go look at the information on the conformal transducers, basically they're designed to match both the taper of the cartridge case and the curvature of the cartridge case in the circumferential direction, and it leaves this little. I don't believe it's even a thou proud bulge as a result of the case contacting the face of that transducer. So folks see this is what they're dealing with.
Now, does the location vary on testing? I know Sammy has their specifications of where the transducer is placed.
I'm going from memory here, so don't quote me. But I believe the SAMI specs say that it's a certain distance back from the shoulder brake there.
Right. The CIP has theirs.
Yeah,
Which is
CIP,
the-
I think, does case mouth.
Okay.
Okay.
And then the military has theirs. And I
And
don't
the
know.
mil-
I don't know what the military is. So
and yeah, and I can't. I'm trying to remember if I've ever seen that. Like I've been to Lake City, and I'm trying to remember if I saw what they do, and I'm drawing a blank. Sorry.
yeah, that's okay. I mean, I just know that the military has their own way because they're, it's the weird thing. Like the military measures a velocity at 78 feet from the muzzle. Um, so you're getting a, a 7.62 by 51 ball at 78 feet at 2750.
Why? You know why it's 78 feet, right?
No,
It's 1,000 inches.
okay.
And now you know.
Now I know. Okay, yeah. But we're all sitting there looking at 10 feet from the muzzle with the
Right.
sky screens, or radar is measuring out however
Yep.
far it's going to go, or
Yep.
a magneto speed is right at the muzzle. And the military gives us this at 78 feet, and we're all sitting there trying to
Back it up to the muzzle.
work it back. Yes.
Yep. Yep. Yep.
So
Yeah. So once upon a time, I worked on some pretty high medium cal velocity ammunition. The muzzle velocity was supposed to be 5,000 feet per second, and we went through some pretty significant hoops comparing the muzzle velocity measurement scheme at the gun house versus the ammunition producer. The ammunition producer was using magnetic coils. The bullet was steel, so magnetic coil worked just fine. But the separation between the coils was still, if I recall, 20 feet. And you needed to have that separation in order to get the resolution you needed to get the accuracy on the velocity measurement. And what the gun house ended up doing was putting 5 Ayler light screens in series and doing kind of a
proof channel.
No, more of a, we're going to fit the time displacement back to the muzzle and come up with a velocity that way.
Oh, okay.
And we were, our error measurement was like under 2 feet a second. So we had a pretty good handle on, even though the velocities were high, we had a pretty good handle on what the actual velocities were.
That chronograph had to have a pretty fast clock in it then.
Yeah. Yep. Of course, this was 40 years ago. So
Yeah.
anyway, all right, let's go on to the next slide. So this is what happens when you fire a 9x19 cartridge in a 357 SIG, and you can see the thing looks like a pregnant guppy. And sad to say, I was the culprit that was involved with this. And we were at the range with some friends, and like, oh, well, damn, it won't fire again. Like, what the hell's going on? And you give the sliding yank, and it won't move. So after a little bit, we did get it to move, but yeah. So the residual stresses were pretty high, and I was actually very impressed that the cartridge cases didn't rupture.
I've seen that before, and by knowledge, I know of firing a 41 Magnum and a 44 Magnum.
Oh.
And all I've seen is split the case.
Oh,
That's all
okay.
it did. So, um,
I've done that, but it was a 40 inside of a 45. That did
Oops.
split the case.
Yep.
I did it on purpose, though.
Okay. Well, I wish I had, I could take credit for having done this as an experiment, but there was no intention there, unfortunately.
uh,
Okay. So folks talk about annealing all the time. And the thing I always worry about is this hardness profile. So for all brass cartridge cases, there is a hardness profile as you go from the back end to the case mouth. And in the upper left-hand side, you see the cartridge case hardness profile, the upper and lower boundaries. And you're cautioned, if you look at the cartridge case drawing, you're cautioned that you dare not have a sharp discontinuity in the hardness profile. And the red line there, the red dots with the red line show you a hardness profile that met the boundaries of the drawing, but the gradient was too steep. Kind of, let's just say, a few tenths of an inch back of the base of the shoulder. And the effect of that is what you see over on the right hand side. There was a cartridge case separation during what they call function and casualty testing. Okay, and function and casualty is just a basic. You put 100 rounds in a belt, you fire through the machine gun. Did the machine gun fire all 100 rounds with no troubles? And if the answer is yes, you ship it. It's not the only test that gets done, but you have to pass that test in order to accept the lot. Okay. And in this particular instance, the hardness profile was incorrect, and they failed the lot. Oops.
yeah.
Those are expensive failures because there's lots of ammo tied up.
Now, are we talking the difference between what the brass started out as and to what it was annealed as?
No. This is
Okay.
the as made
Okay.
hardness profile. So what they did was they basically took cartridge cases, they sectioned them longitudinally, they prepared them in an epoxy matrix, polished them, and did micro hardness checks along the case wall, going from the base to the case mouth.
Okay.
Okay. And this, really sharp, abrupt knee in the curve that you see for the red line, a couple tenths of an inch back is kind of what they found. And like no kidding, you've got the hardness profile is meets the drawing, but it's not correct because you failed the function and casualty testing.
Okay.
So if you change, so annealing, I've never seen, I'm just thinking back on the memory banks here. I don't think I've ever seen anybody fail a cartridge case because the shoulder was too soft. Okay.
Mm-hmm.
But you definitely, like down in the extractor groove, don't touch that thing. Don't try to anneal there. It causes you all kinds of grief.
So you're saying this is an abrupt hardness change?
Yep.
Okay.
Yep.
Yeah, this shows a lot.
That's another reason though, when you anneal to turn the case.
Yep. Absolutely. A buddy of mine's got one of the ugly annealers, and he let me borrow it for some stuff that I was working on, and You know, I set it up, read the directions, watched a couple of YouTube videos, and like, you know what? It's a good rig. If I shot more, I'd have one.
Hmm.
So yeah, I mean, good rig. It leaves a nice visible signature that it's been annealed.
I use one all the time in reloading, and after every shot, it gets the case gets annealed.
Yeah.
It just that's the way I work.
Yeah.
So, and I have found that everybody says 750 or so for a template, and I run 950 because I feel that it needs the how do I put it? The induction annealers that are out there,
Yep.
they hit a higher temperature than the the torch type do.
Yep.
But they do it so fast that you don't see it, and a 950 temperature annealing brings it more into line with what an induction annealer would be.
Okay. Yeah, I wish I had some firsthand experience with this, but I don't. With the annealing process itself, I don't have any firsthand experience other than running my buddy's ugly annealer.
What's Lake City doing? They flame anneal or do they induction?
It's induction.
Induction, really? Okay.
Hang on. So for this 762 line, it was induction. I did see. Trying to remember. I did see the 556 line, and I'm drawing a blank on what that one was. That one might have been gas.
Yeah, I watched somebody's video. I watched somebody's manufacturer's video a while back, and they were doing a flame anneal. So
Yeah. So either way will work, but you got to have testing equipment in order to do the hardness checks to make sure you know what you got from your process.
yeah.
What I've seen is using both. The initial slug gets annealed flame wise, and then starts to get work hardened as it goes through, and then induction annealing after that.
Oh, interesting. Okay. They must think that they can control it better with induction, I would guess.
Mm-hmm. Yes.
Okay, shall we go to the next slide?
Yep.
Okay, so this, sorry for the blurry picture, but this is another photograph of the a case neck split. That this was one of those 2506s that I had converted from Lake City 30-06. And in doing that resizing operation, you have to do an intermediate. In this case, I did an intermediate to 270 first, and then 25-06. And and when I did this, I knew nothing about annealing cartridge cases. I built a bunch of ammunition, sat around for a while, and this case split as a result of the bullet being pressed into the case mouth. Just high residual stress, and the case didn't like it, gave up the ghost.
And annealing would have fixed that.
Annealing would have fixed that.
Yeah.
Okay.
Yep.
So now I'm going to show you a few slides on something that I ran across. I haven't been able to get any traction getting people to look at it, but there's a custom, high-end custom 1911 gun maker here in the northwest corner of Vermont that has run into this, and he mentioned it. My wife had to be doing work for him. I went in and introduced myself and talked to him a little bit, and he mentioned this particular problem, and then he dug up some samples for me, and I started kind of turning the crank a little bit, see if I could figure out what was going on. Okay, so the first thing that happened was there was the case ruptured, and basically the bottom of the barrel is fairly unsupported, and it vented out the bottom of the cartridge case and caused an uncommanded mag dump on the ground.
Yep.
Okay. So the evidence of exceptionally high pressure is definitely there. The primer pocket diameter is 0.227, and it should have been 0.210. And then the web distance, the distance between the back of the cartridge case and the interior cavity of the interior cartridge case was 0.122, and other federal Smith & Wesson cases were 0.168. So there's, you're left with the conclusion, definitely high pressures. Like, okay, and this happened on a very, let's just say, infrequent basis, okay? So the brass yield strength is about 65,000 PSI estimate. The ultimate strength's around 95,000. Again, that's an estimate. Elongation of failure is about 6%. And so the question is, what the heck caused this failure? Okay. And so I started scratching my head, and I came up with this little silly idea. On the upper left-hand side is a before firing picture, and it shows the cartridge, a section of the cartridge in the chamber, headspace properly and seated, and there's a gap between the OD of the cartridge case and the ID of the chamber, okay? And particularly if the cases are thin-walled, you can run into this, okay? And so on the right-hand side is during firing, what happens is the case wall mashes out and hits the chamber, and now you've got this sharp corner that is exposed to the bullet jacket, okay? And particularly with plated bullets, not jacketed bullets, plated bullets. So the plated bullets are kind of like, you can think of it as toothpaste in a tinfoil sack. Okay, so you've got a very thin, like 4,000 thick plating of copper on it, and because it's plated, it's dead soft. Okay, so you can't count on that copper plating to provide any strength whatsoever. So if that sharp corner is exposed to the jacket, that thing's going to dig in and grab the bullet, and it's going to cause the pressures to spike. Okay, so that's what I believe. And there might be other things, like maybe the bullet got stubbed during the feed cycle and pushed more deeply into the cartridge case, and that helped to contribute to the high pressures. But it's really I think it's the exposure of the copper to the sharp corner in the chamber. You go to SAMI, you look at those chamber interfaces. They don't say break the corner. They don't say put a 5,000th radius on it. They don't say put a chamfer in there. They don't specify. Okay, so it's my opinion that the sharp corner there could cause trouble. Okay, and this is an article I happened to notice in Shooting Times magazine on May 2016 issue, and Black Hills load I mentioned displayed an odd anomaly. Thin rings of copper material were left behind at the forward edge of the chamber every couple of shots. The rings prevented following cartridges to chamber fully. Blah, blah, blah. Okay, so it apparently does happen. So, but for whatever reason, this guy happened to get away with it in terms of not causing an uncommanded mag dump.
What I have found in the 45 ACP and the 1911 series
Yep.
is that they have supported chambers and unsupported chambers.
Okay.
And you will find that in an unsupported chamber that the bottom of the back of the case will give out in high pressure loads and cause that mag dump, as you call it.
Yep.
The difference in a supported chamber on my supported chambers on my left and unsupported chambers on my right. If you notice the difference in the two slides, two barrels, it this one here supports the case up farther. This one here doesn't support the case as well. I don't have a 38 Super with me right now, but here is 45. And let's get a picture of this. Here at the mouth, you see that the case is unsupported at the back end here.
Yep.
And it will give out if the pressure is over 25,000 PSI, which you can do with a hot load.
Yep.
So I have run 38 Supers in the 45,000 PSI range. And with a supported chamber, they're fine. With an unsupported chamber, they're not fine. And Colt is the biggest killer of the 38 Super because its barrel is unsupported, and it will do nasty things to you. Packmeyer grips are a great thing to have in a 1911 with 38 Super and a Colt barrel because they have a metal panel that's built into them. Ask him how I know.
So there's a question here. Is it better to bring up the temperature quickly or slowly? He's using a flame annealer. I don't have any firsthand knowledge there. I can't answer that.
You go too slow with it, and what's going to happen is you're going to transfer too much heat to the back of the case. So you want to bring it up quickly.
Makes complete sense. All right, and then there's another question about how does bulge busting cases weaken them? Basically, it doesn't weaken them. It work hardens them, and then you lose elongation at failure. So that's the trade-off.
So if you're bulge busting, you better be annealing.
No.
You better no. I think the better solution is to limit the number of times you bulge bust.
Yeah.
I suppose you can't really anneal a pistol case because you'll hit
No.
the web.
No, don't do it.
Actually,
So
if you're doing standard loads and you start to see that bulge, I'd just pitch the case, especially 9mm. Unless you're really loading pretty hot rounds.
In 38 Super, if you're loading hot rounds, you get two reloads on it, and that's it. If you're shooting 9 major, you're going to get 2 loads, and that's it. You're not going to get anything more out of it. So, and you're talking, in the 40,000 PSI and above range in those type of cartridges. So because you're looking for the gas in order to make the compensators work. You need that gas to make a compensator work. You need the high pressure gases to affect the compensator and make the gun recoil the right way.
We ready to move on?
Yep.
Okay. So this is a little graphic I put together that shows the different propellant geometries that are available to us as reloaders. You know, going from left to right, we have flake, sphere, cord, single perf, and a type of propellant that's still hasn't kind of muscled its way onto the stage yet, but is I've had a little bit of experience with, called C4. Basically, C4 is a cube with 4 perforations in it. And the C4 was interesting because we did a big it's called the design of experiments, trying to figure out what combinations of things work best to get the group small for sniper ammunition. I was working with Lake City, and the C4 did a great job in terms of getting the group small, but it had issues with the primers that we were using in terms of muzzle velocity variability. The muzzle velocity standard deviation for the C4 was, kind of up in the double digit range, and they were looking to get down in the single digits. And for whatever reason, the C4 didn't like the primers that we were using, and we didn't have a particularly large selection of primers that we were playing with. So for whatever reason, the primers we were using, it didn't particularly care for in terms of velocity variability. Okay. The cord powder is used, from what I've got that listed as typical use for rifle. I've since learned that that's actually should be pistol. I know Vita Vori makes a cord propellant for pistol applications. They also claim to increase the quote unquote porosity, which I don't really think I understand very well. But that's another geometry option for folks. But it's much less commonly used than the flake, the sphere, or the single perf geometries. And up at the top, we've got kind of what chemistry is each of the powders is being can employ. And the single base powders are basically nitrocellulose only as the primary constituent. There are other things in it like stabilizers and deterrents and that sort of jazz. Double bases use anywhere between I'm going to pick a number, 8 to say 12 or 13% nitroglycerin in addition to the nitrocellulose. So that's kind of what's available to the shooters. Okay. And double base powder, because the nitroglycerin has more energy than nitrocellulose, you get about 10% more energy, which gives you more, has the potential to give you more velocity.
Now, how does it affect the barrel life?
Like anything else in life, there's no free lunch. So the nitroglycerin increases the flame temperature of the propellant, which makes the barrel life shorter, generally speaking. I mean, so barrel life is really largely determined by the firing schedule. How fast are you firing? How much propellant pushing out through the barrel? and how hot does the barrel get? What surface treatment does it have? Does it have chrome plate? Does it have nitride? Does it have nothing? Um, um, so that's part of the determining factor, but kind of with equal schedules, you'd expect the barrel to not last as long using a double base powder. And I guess I can't tell you what the relative life ought to be.
How can you?
Yeah, well,
Because
yeah,
what's the
it,
firing
yes,
schedule? You know, that's,
yeah, exactly.
you know, I can tell you that you go out to a prairie dog town, you go out with one rifle and you sit down with 500 rounds of ammunition, and you can shoot that all in one day, and you can put a lot of heat through that barrel and
Yep,
shorten its life. Whereas you know, you go out to the range and you take your time and you shoot, you know, one round every 2 minutes to print a 5-shot group. um, you know, you're not putting a lot of heat into the barrel. So
right, absolutely. So, if there are no questions here, we'll trudge onward. Okay, so this is a little graph I put together that shows the surface area to volume ratio as a function of the web size. So the web dimension is the physical feature on the propellant grain, the smallest one that needs to be burned in order for the propellant to be completely consumed. Okay. And so if you look at the different propellant geometries that are out there, there are flake powders, ball powders, tubular powders. Um, they kind of fall into groups. Okay, so the flake powders are on the left-hand side. You know, they tend to be typically very small web because their usage is in low pressure items like pistols and shotguns. And ball powders and extruded powders or tubular powders are used in much higher pressure systems. And this graph is all keyed by the different propellant manufacturers that produce powders. There's St. Mark's, there's IMR, Alliant, Norma, and Hodgdon. So they're all in here. Okay, and obviously the peak pressure affects the choice of the powder geometry, and in order for us to get the muzzle velocity as high as possible, you need to run pressures to the upper limits of the firearm design. So let's just say that the design working pressure is 60,000 psi. You want to have your average load be up around 57-ish if you can manage that. And assuming that your variability is kind of small in the 500 to 750 psi range. Of course, we can't measure that. You have to be able to measure velocity, and hopefully they correlate. And in most cartridge cases, they do correlate pretty well. Okay. So different bullet weight and construction, copper jacket, lead core versus monolithic copper bullets, that affects the peak pressure. No surprise there. And the other thing that you need to worry about is you'd really like to have the powder completely burned out while the bullet's in bore to extract maximum velocity out of that powder. Okay. And powder burnout affects muzzle flash. Burned out's good, not burned out adds to the flash problem. Okay. So Are there any questions here?
Not currently.
Okay, we will move on. What factors increase peak chamber pressure? Okay, increased powder charge, no surprise there. Use of identical charge weight of powder with an increased relative quickness, again, no surprise. Increased mass of the projectile, again, that bullet can't accelerate as rapidly as a lower mass projectile. So the volume generation rate behind the bullet is going to be lower. That's going to cause the pressure to increase. Okay. Increased bullet engraved length, that's going to drive the resistance, inbore resistance pressure up. That's going to cause the peak pressure to spike. Excuse me. Increased bullet stiffness, in other words, all copper versus a cup and core jacket, that's going to bump the pressures up. Okay. And yes, guys put, particularly Barnes and Hornaday on their monolithic copper offerings do put cantilevers in there. Basically, it's a receptacle for the displaced jacket or body material to be pushed into, and that helps reduce the engraving pressure, but it doesn't it's not 100% effective in terms of getting it back to cup and core kind of levels. Okay. Decrease free run to the start of engraving is going to boost your pressures. Decreased internal case volume relative to a baseline will increase your peak pressures. And obviously, decreased barrel internal dimensions will drive up the resistance pressure and then also increase your peak internal pressure from combustion. So in the block there down below, changing loaded cartridge length is complicated. Okay, longer loaded cartridge length means more chamber volume, which would tend to give you lower pressure. But it also comes with shorter jump to the rifling, which gives you higher pressure. Your results are going to depend on the bullet, powder, and cartridge details. Okay? So you have to, there's not a good answer for if I load my bullet out, am I going to bump the pressure up or am I going to reduce it? There's no one size fits all answer for that question. Questions here?
No, sir.
Okay, we'll move on. All right. Why do some powders shoot smaller groups than other powders in my rifle? So this is a little bullet barrel powder interaction study that I did. I had been yakking at the guys at Hornaday a little bit, and they said, "Oh yeah, changing the powder changes the dispersion." And I was, for a very long time, I was of the camp that powder is just a push. How can it affect the dispersion? And so I started looking into it. We have a what's called an inbore balloting code. It looks at the dynamic interaction between a flexible projectile and a flexible gun tube. Okay. And so you can put in different propellants and look at what the dynamic response is for a given powder in a given barrel with a given bullet. And so that's what I did here. So I looked at H4350, W760, H100V, and Varget. Okay. And each of these had a slightly different average muzzle velocity, and the muzzle velocity variation that you see is unique for each propellant. So the H4350 had a muzzle velocity variability of 8 feet per second. The W760 had 15 feet per second. The Vargot had 4 feet per second. And the H100V had a velocity variability of 10 feet per second. And so let's talk about all the graphs here with the blue dots and the orange dots. So the blue dots are what's called the yaw rate. That's the wobble of the bullet as it initially exits the barrel. And that's one of the primary sources of the fall of shot scatter at the target. We know it's dispersion. Some folks call it accuracy. It's not accuracy really, but so you know, and at zero, in the middle of each of these charts is the average muzzle velocity, and then we go outwards from there, left and right. There's plus and minus 1, 2, and 3 standard deviations or sigma from the average. So that's the variation that you're going to see as a result of firing lots and lots and lots of bullets. Okay, and you can see that, like, well, I'm going to just pick on the H4350 for a little bit. So there's, you know, it's pretty easy to see that there are waves in that response map. So there are, you know, like just shy of -1 standard deviation in muzzle velocity. There are some bullets that are going to come out with very small initial yaw rate, or yaw rate's a good way to put it. Okay, and then some of them are going to come out with, you know, fairly high yaw rate, around 8 radians a second. Okay, and so it's a luck of the draw which one you're going to get. And if you go closer to zero, there's this little spot just shy of zero where kind of everything is under 4 radians per second. So you know, you're going to think you see patterns, and folks call them nodes. Nodes are velocity nodes, particularly, are garbage. Dispersion nodes are probably real, but you kind of can't, because you can't get the velocity variability to zero, you can't access these nodes and plan to live within one. Okay? So that's the blue dots. The yellow dots or the orange dots are what's called the cross velocity. So that's the bullet just translating laterally sideways. And this could be left, right, up, down. It kind of doesn't matter. And with the yaw rate part, the wobble part, those also can be kind of anywhere around the clock looking downrange. So this just tells you kind of what the absolute values are. It doesn't give you any sense for direction or it does tell you magnitude, but it doesn't tell you where these bullets are going to land. Okay, but it's interesting to note that the responses for the different propellants are kind of wildly different. And that's why changing the propellant can have such a large effect on the dispersion behavior we see for our bullets.
So, Rego Frego has a question.
Okay.
I'm just trying to figure out where the echo is. Maybe it's just me. So I have a question about
I'm sorry. Okay.
I ran up ladder loads for a 300 blackout using Barry's copper-plated 220 bullets in an 2015 with a 10.5-inch barrel. He used 4 different powders.
Yep. Yes.
Okay.
And
How
what?
about the second part first? So he used 1680, 4227, CFE black,
Yep. Yep.
and SW black. The first 3 were pretty consistent on paper at 50 yards. The SW black, however, was the first load. First, excuse me, the first load was low, nearly 2 feet, but velocity was only 100 to 150 foot-pounds or feet per second difference.
Yeah.
880 FPS average, if I remember right. The odd thing is when I had the ladder load, as I went up the ladder load, it got closer to the grouping where the others were, but it was supersonic by that point. Is that something to do with the pressure curve of that powder?
And he's talking impact points, right?
Yeah.
Yeah. So that's the impact point is a function of the bullet barrel interaction and where the barrel's pointed as the bullet leaves. Okay. And the it's the gun recoiling and rotating and the whole bit. So there's a lot to the dynamics there. What about group sizes? Did he say anything about group sizes?
No.
Okay. All right. So 300 Blackout is one of my least favorite cartridges for a lot of reasons, but one of the reasons I think is the fact that it doesn't have much of a shoulder, and that doesn't do a very good job of restraining the propellant during the combustion process. And so I don't think I have it in this presentation. I have it in other presentations. You compare the correlation between pressure and velocity for most bottleneck cartridges, and the correlation's pretty good. For 300 Blackout, it's just horrible. It's like there's 2 different populations. And I attribute that to the propellant being able to wander around in the cartridge case during the ignition and combustion phases. So one of the things you might think about doing with a cartridge like the 300 Blackout, if the cartridge case is not filled, I mean, I'm talking if it's less than like 90% filled, you might think about putting in some sort of an inert filler. We've successfully used baby cereal, dried baby cereal in the past. Cotton batting might do you okay. Just something to restrain the propellant during the ignition and early combustion phases.
All right.
Okay.
He says the 1-inch group for most groups, but the SW Black performed worst. Best group is 1.75.
Yeah, so one of the things you got to worry about, particularly with 300 Blackout, it tends to run at lower chamber pressures than others, which means the propellant burnout is going to be kind of much more difficult to achieve. I would suggest that he look at powders that are kind of closer to the faster relative quickness side of what's acceptable to load.
Okay.
Okay.
And then I have a question from Rumble, which I can't put on the screen, but it's how do we find out what powder reached full burn in the common barrel lengths for common cartridges? I think he's talking about the burn rate chart from earlier.
Yeah. So one of the things that you could do is to make yourself a little frame out of some pretty hefty plywood and either bolt it or clamp it or weight it to the bench that you're on and cut a little hole in it for the bullet to fly through. And then staple some white cardboard to the face of it facing the gun. And if you have a muzzle brake or a suppressor or something like that, take that thing the hell off and then fire through that hole in the plywood. And you're looking for little divots in the white cardboard to tell you whether or not the propellant's burned out. Okay, so if you see a lot of divots in the white cardboard, that indicates that the propellant is not burning out, and you want to probably switch and move to something kind of crowding faster relative quickness. So the problem with the relative quickness thing is the fact that there's two things that affect that. The first is the web, and the other is the deterrent level. And a deterrent is a coating that the powder manufacturers put on the propellant to slow its burning. Okay, and so what you really want to maximize velocity is something with a small web but high deterrent. The problem with that, of course, is the fact that you're probably going to want to use a magnum primer to light it off. It's going to be hard to ignite. Okay, so and particularly for subsonic bullets, you want to really crowd the faster end of the relative quickness scale to help with the propellant burnout. And I mean, I've got some information on web, and suppose if I picked through that information, I could kind of, I've got the propellants characterized. I suppose I could go say, okay, this has got a web of this, and its relative quickness ranking is that. That means it's got to have more or less deterrent level. You have a better chance of burning it out. I mean, something that would take a lot of effort to do. Other questions?
Nope, that's all for now.
Okay. All right, bullet construction details. I mean, these aren't any secrets probably. There's cup and core bullets, there's plated bullets, there's bonded bullets, there's partition bullets and monolithic bullets. That kind of covers. There are frangible bullets as well. Didn't cover those because they're not very interesting. So the cup and core, basically you've got a cup of gilding brass. It's a copper alloy. And you smash a bit of lead into it, and then you do some subsequent forming operations. And typically these things have a jacket thickness between, I'm going to pick a number, 10 thousandths and maybe 35 thousandths thick. Okay. And you've got, because you've done cold work to that jacket, they've got a fair amount of strength. Okay. In contrast to the plated bullets, which, they're typically lead with a 3 to 4 thousandths thickness of copper plated on their exterior. And the plating process makes that copper absolutely dead soft. So when I mentioned before, it's like toothpaste in a bag of tinfoil. That's not so far from the truth. Okay, so these bullets don't have a lot of, let me use the word structure or phrase, structural robustness. Okay, I did a job for a company that was doing a development on 9mm handgun last year, and they were very happy with the accuracy of the handgun, the group sizes that resulted, with the exception of one manufacturer that happened to use a plated bullet, and it was kind of a let's just say budget-minded offering. and for whatever reason, they could not get that bullet to group. And so we looked at the dimensions of the barrel. Turned out that the lands were a little on the large side. The grooves were really on the large side. But that turned out wasn't the issue. There was some issue with, let's just say, roughness in the forcing cone of the barrel. And that turned out to be what caused them grief with the plated bullet. They swapped the barrel out, problem went away. Like, okay. So I don't think we need to cover any more here unless people have specific questions.
Nope.
Okay, we will move on. Okay, rifle bullets and ballistic coefficient. So here I've got 3 different 30 cal bullets, 170 grain flat point, 178 grain ELDX, and a 220 grain ELDX. Okay, and I've got kind of some recommended usage ranges listed along with the twist rates that are required for gyro stability, and then a comparison of the G1 ballistic coefficients. So for the flat point, it's 0.189. For the 178 grain ELDX, it's 0.552, and for the 220 grain, it's 0.65. Like, okay. So the length affects the rifling twist required for gyroscopic stability. The longer bullets require faster twist. In other words, lower number of inches per rev. Okay. And the BC is really a measure of velocity retention. Higher is better. It also gives you less crosswind sensitivity. And it's proportional to the weight divided by the product of the drag and the area. Okay.
Yep.
And I mean, until like a year or two before my retirement, I never dealt with ballistic coefficients at all. We taught drag coefficients. Ballistic coefficients kind of you could say a contaminated term because the weight and area are in there. We tended to not deal with that as an engineer. Okay, why is ballistic coefficient important to rifle shooters? Well, I've got 3 graphs here: velocity range, drop range, and crosswind drift versus range. And you can see that with the 220 grain and the 178 grain, the velocity retention is, not identical, but fairly similar. And with that flat point guy, you know what? He loses velocity damn quick. So, just if you want good velocity retention, you got to go with a high BC bullet. End of discussion. The drop versus range, kind of a similar story, although I launched all of these bullets at the same 2,700 feet per second initial velocity just to make the comparisons on the BC side fair. Okay. And you can see on the drop versus range graph that for the 2 high BC bullets, out to 1,500 feet, 500 yards, that drop is just about dead nuts identical. And the flat point guy really pays the price for having high drag. Okay. And over on the right-hand side, crosswind drift. So this is the drift of the bullet in feet due to a 10-mile-an-hour crosswind. So 1,500 feet, 500 yards, that's a pretty long poke for us Eastern boys. I don't know about guys out west, but that's a fair poke. The two high BC bullets, the 178 and the 220 grain, they're pretty close to one another at, right in the 1 foot, a little over 1 foot wind drift due to that 10-mile-an-hour crosswind. But the high drag bullet, the low BC bullet, instead of a 1 foot drift, you've got over 5 feet. So this is a pretty graphic demonstration of why you really want to have high BC bullets if you're going to take things long range.
Okay.
Okay.
Yeah.
All right. Let's talk everybody's least favorite topics here. Shotgun slugs.
I like shotgun slugs.
Do you? Well,
yes.
Okay. All right. So the Foster slugs are a bit of a, I think the word I want to use is enigma. So they start off as this, kind of hollow based dome shape that you see on the far left-hand side where it says Foster slug. And, it's got a big cavity in the base. I know Federal uses what they call their true ball design, where they put a little plastic ball underneath that thing to help it maintain shape during the launch. But basically, the lead has such high density, such low yield strength that it when it exits the tube, if doesn't have that little true ball underneath it, it's going to come out like the picture in the middle there. It looks like a dinner plate flying flat face on. And so as a result, that is quite high drag, which limits the range, which is one of the desirable features of it. But it also doesn't have anything for stability. It doesn't have gyro stability. It doesn't have static stability. The only reason that it is able to do what it does so well is it's flat. Okay. In other words, as the bullet yaws, as it tilts relative to its velocity vector, it can't generate much lift to swerve the thing off the flight line. Okay. And if you go look at Tau Flatermouse on YouTube, he's got a high-speed video of Foster slugs, and they do rotate, but it's pretty slowly. Okay. So that helps from a dispersion standpoint, group size standpoint. But it's not enough spin to actually stabilize the bullet. Okay. Yeah, so their Foster slugs are a bit of an enigma. It's kind of shocking that they work as well as they do, in my opinion. And contrast that to things over on the far right-hand side for rifle barrel shotguns. I've hunted with the AccuTip and the Federal Trophy Copper, and my opinion, those work pretty damn good. If you're in an area where you can't use a rifle, out to 125, 150 yards, you don't give up a whole lot, in my opinion, by being restricted as long as you can use a rifle barrel in your shotgun.
I did some experiments with a 20 gauge, and I had a 20 gauge Mossberg with an 18-inch barrel, but it was rifled.
Yeah.
And then I had my 870 with a 28-inch barrel.
Yeah.
Shooting Foster slugs, and even though I had 10 inches shorter It was incredibly more accurate at 100 yards.
Interesting.
So the I use the
You didn't
Hornady.
did you happen to get velocity information out of those?
No, I didn't have a chrono with me that day.
Okay.
Hornady SSTs is the sabos I was using, or sabots, however you want to call it.
Sabo. That's in the business we call them sabos, not sabots.
Fantastic.
There you go. Okay, so you could probably get away with using a Foster slug in a rifle tube, but don't use a Sabo slug in a smoothbore tube. You will not be happy.
It does not turn out well.
Yep. There's no spin for gyro stability. There's nothing to peel the sabot open to let the projectile loose. Blah blah blah. It's just don't bother. It's a waste of money. Any questions here?
No, nothing right now.
All right. Okay, gyroscopic stability equation. So there's a few things in here that folks might think about when they're going to load bullets and whatnot, or think about what I got to do to get my bullet quote unquote stable. So and this is not Miller's stability equation. This is the gyroscopic stability equation. This is how the professionals compute the stability. Okay, so in the numerator, there's a 2 factor in there, and then there's the polar moment of inertia squared, I sub x, and then the spin squared. So if you increase the twist of the gun, the stability goes up by the square of the spin. So you've got a pretty big lever there. Okay. In the denominator, you've got pi. That's everybody's favorite ratio of diameter circumference on a circle. You have rho 0, which is the air density at the gun muzzle. You have I sub y, which is the transverse moment of inertia. So that's the resistance of the projectile to being dumped over, perpendicular to the longitudinal axis. We'll talk about that more in a minute. And then you have C sub M alpha. That's a pitching moment coefficient derivative. And we'll talk about that in a minute too. You have diameter, and then you have velocity squared. Okay. So let's talk about the transverse moment of inertia first. Okay. So the transverse moment of inertia is the resistance of the bullet to being oscillated in an axis perpendicular to the longitudinal axis of the bullet. So if you thought about, let's take a barbell, and we'll hang it from the ceiling with a wire spring, and you displace that barbell, and initially we'll have the weights all the way at the end of the bar. And so if you displace it and let it oscillate, that thing takes a long time to oscillate. So that's a situation where you have what we would call a high or a large transverse moment of inertia. Okay? If you took the same weight, the same barbell, and you take those weights, and instead of having them on the end of the bar, you smash them right close to one another, right near where the spring is, now that thing is going to oscillate much more rapidly. So now you have a low transverse moment of inertia. Okay, you have low resistance to being accelerated. Okay, so that's what the transverse moment of inertia is about. The Cm alpha, the pitching moment coefficient derivative. Okay, in any spin stabilized bullet, there's a center of gravity. That's where the bullet balances if you put it on a knife edge. And then there's there's a normal, what's called a normal force center of pressure location, and that's forward. It better be forward of the bullet center of gravity. Okay, so that separation between the CG and the center of pressure location in calibers multiplied by another aero coefficient called the normal force coefficient gives us this CM alpha term. Okay, and it's you can think of it as stability. Okay. Now, the bigger you make the CM alpha, the smaller you make the gyro stability. Okay. And we'll talk about the effects on dispersion on another podcast, perhaps. Okay. So, but looking at the spin squared to velocity squared for a given rifle or given handgun, given weapon, that ratio of spin to velocity is fixed because the rifling is fixed. The only way you can really change the gyroscopic stability is by changing the velocity and how that affects the pitching moment coefficient derivative. That's a function of the Mach number. Okay, air density is in there as well. The higher the air density, the lower the stability. Okay.
Okay.
And from a design standpoint, that's a gyro stability of 1.4 to 3.5 in most atmospheric conditions is typical, with an air density of it's 1.2, and the units are kilograms per cubic meter. Okay. When a bullet enters high density material like water or tissue, that material density is 1,000 times larger than the atmosphere. So your gyroscopic stability is much, much less than 1. And that's what causes the bullet to tumble when it enters high density material.
Okay.
Okay.
Oder Sigerson has a question about the equation. He says, this is all nice, but where does one get those numbers from?
Yes. So if you have a CAD modeling system, you can get the inertias. Okay. The CM alpha, you need an arrow code. And this was in here to illustrate the effect of changing the density of the medium in which you're flying.
Okay.
That's why I included it.
So my question is, how does the Miller formula relate to this?
Miller formula is garbage.
Okay.
Don't
All right.
use it.
Don't use
Unless
it.
I mean, if the zombie apocalypse is upon us, then you can use it. But
Okay.
okay. I've actually started some work on a different formula to see if we can't do something better than Miller. And it's one of those you put it down and then walk away and forget about it. And I haven't picked it up in a while. But yeah, the Miller formula is much less than ideal, and it's much less than accurate. The reason for it is it doesn't take into account the inertias.
Okay.
It doesn't take into account the air density, and it doesn't take into account the effect that different bullet shape has on the pitching moment coefficient derivative. So it's really a stopgap measure. It's much less than optimal.
So
I wish I had better recommendations for you, but I don't at the moment.
no, I understand. I'm just sitting there going, and I'm going to look. So it asks for bullet length, muzzle velocity, barrel twist rate, temperature. So yeah, there is no.
There's no temperature doesn't give you air density.
Right. It's asked for
You
pressure.
need pressure. You need pressure as well.
Yeah, it's got pressure in there, but it
Oh, does
doesn't
it?
have. Yeah, it doesn't have the ballistic coefficient or anything like that. In
Yeah,
order to.
the ballistic coefficient is not strongly related to pitching moment coefficient.
Okay, but I mean that would tell you to at least give you an idea of the shape of the bullet, right? I mean, I know it's not a drag model, but it would help. So I'm just looking
Yeah,
at
so
it.
the problem is that you really need the separation between the CG and the center of pressure,
Okay.
and that's really related to the mass distribution within the bullet and the length of the bullet. Now the length is in there. That kind of covers two factors. That covers the separation between the CG and the CP, and it may cover the transverse inertia some. But it still doesn't take into account the effect that the shape of the ogive. So whether you have a tangent ogive, a secant ogive, a hybrid ogive, or a conical ogive on the bullet, all those have, for the given ogive length, they all have a different center of pressure location. So it's like, well, okay, if you're not distinguishing amongst the ogive shapes, you don't have a snowball's chance in hell of predicting the actual stability of the bullet.
Okay. I'm asking because one of the older cartridges that we use, the 22-250, always
Yep.
came with a 1 and 14-inch twist barrel. And I sit down and
That was done. That was done for dispersion purposes,
okay,
and they only fire like really light bullets, like 55 grain bullets. I
right,
don't think they can't fire 60s. The twist is too slow.
right. So, but nowadays with modern bullets, they're longer, and the
Yep.
Miller formula comes out and it tells them it's unstable in
Yeah.
a 55 grain bullet. Whereas some of the older flat base bullets, they still work, but anytime you throw a boat tail on it, the bullet becomes too long.
Yeah. So what happens with the boat tail is the boat tail kills the lift on the back end of the bullet aft of the center of mass. So when that happens, what it does is it pushes the normal force center pressure forward, which makes CM alpha a bigger number, which drives the stability down.
Okay.
Okay, so that's why that happens.
Okay.
So if you tried the bullet, it could be same mass bullet, but without a boat tail, you might have success.
I just found that the bullets are just too long. I mean, I just from what I'm finding now, that I have to go to old bullets that are not ballistically efficient compared to what's out there. So that's so the Miller is worthless. Okay.
Well, if it's all you had, yeah, go ahead, use it. But it's not anything I've ever used professionally. Let's put it that way.
Okay.
Okay, and I studied it briefly for inclusion in my book and promptly forgot most of what was in it.
I love it.
Okay, yeah, let's go to the next slide because we've got a little more information there. Okay, so there's really two types of stability that we worry about for rifle and handgun bullets. Gyro stability, is there enough spin to keep the pointy end forward? And then lastly, dynamic stability, does any initial yawing motion decrease with the bullet going down range? Okay. And so across the top, I've got different land and groove diameters, and down the far left-hand column, I've got the twist in inches per rev, and the table is filled out in twist and calibers per rev. And most ballisticians are going to talk calibers per rev. So the stuff in the red is kind of really what I would consider to be very low twist, low calibers per rev, a very slow twist. It's high number of calibers per rev. So that's a very lazy twist, if you want to call it that. And then as you get to the yellow, it's a little bit faster twist. The brighter yellow is faster yet. And then the light green is faster yet. And then the dark green is the fastest thing out there. Okay. And so it just gives you an idea. People talk inches per rev. Inches per rev, if you're talking different calibers, is totally confusing. You need to talk calibers per rev if you want to talk twist rates and compare across different bore diameters. Okay.
Okay. Truth had a question. He says, to go into this much detail, theoretically, how far can you shoot a sabot at sub MOA?
Yikes. Okay. For small cal application, I don't think I've ever seen a Sabo projectile shoot sub MOA ever. I had a box of Remington accelerators that I shot. Golly, it's got to be probably 10 years ago, and I was shooting at a 15 by 15 inch target at 100 yards, and out of a box of 19, I think only 16 hit the paper. So they're not in small caliber. They're not known for particularly good dispersion performance. And part of the reason for that is how they're made. In terms of their structure, in my opinion, they're made with an inadequate structure. Okay, basically, it's just a plastic sleeve, and the back end is in triaxial compression. It shouldn't go very far, but I've never seen one work that's worth a damn. That's me.
So in other words, we have to go to our large caliber smoothbore fin stabilized projectile.
That's a step in the right direction, but there are spin stabilized Sabo projectiles in medium cal that shoot fairly good dispersion. Now let's talk relative numbers. A good match bullet in small cal will shoot around 0.04 mils, one standard deviation. Run of the mill machine gun ammo runs about 0.2 mils or so. Good medium caliber ammo, APDS Sabo projectile shoots about 0.3, 0.35. And that's actually, in the big scheme of things, comparing them to other full bore bullets in medium cal, that's actually very good dispersion. Okay, so I hear small cal guys crabbing about, it's just over one MOA gun, and it's like, you don't realize how good you got it.
I always like it's 1 minute of angle for 5 shots.
Yeah.
Yeah.
Yep.
multiply that by 10, and then tell me what you got.
Right. Yeah. And it's, yeah, it does nothing but grow.
Right.
Yep.
But to go to a spin stabilized, then saboted round in a larger caliber, in a medium caliber, which most of us can't own because
Right.
they don't.
Destructive device, blah, blah, blah.
Right.
Yep.
Yeah. Then there's a possibility you're talking about 0.3, 0.4. So mils, I mean, that's
No, 0.34.
0.34. Oh, okay.
0.34 mil radians. Now that's one standard deviation.
Right.
Yep.
Okay. Which is not that bad. I mean, considering the size.
Yeah. So I worked on, if folks are familiar with a Mark 15 gun mount, it's a 20 millimeter Gatling gun, firing a bullet designated the Mark 244 at about 4,500 shots a minute. And I worked both on the ammunition for that and the barrels for that. And, you know, it shoots pretty good for a Gatling gun. For a
Yes.
Gatling gun.
Yes.
Yeah.
I mean, considering how many barrels in that?
6 barrels, and they're all, I mean, yeah, and they,
Yeah.
I mean, yeah, they've all got to shoot to within a certain distance of one another and all of that jazz. So,
Right. So the
so that
engineering,
was,
the engineering involved in just getting the barrels to shoot in there is extremely high to begin with.
yeah,
And we wonder why we spend, millions of dollars on weapon systems. Yeah.
yep. Well, last ditch, you know, you got a missile coming in, and you got to not only hit it, you got to function the warhead, because otherwise you've got a live warhead on the ship.
Right.
Best case, you got a live warhead on the ship. Right? You don't want that.
Yeah. And it starts out at what, 1,000 yards or something like that, or
a little bit farther than that.
a little bit farther.
Yeah,
Okay.
yeah, they'll open fire at about 2,000 meters.
Okay.
Yeah, about 2,000 meters ballpark.
So, but the timeline between 1,000 meters and 2,000 meters is very short.
Yes, it is.
For an incoming.
Right, which is one of the reasons the rate of fire has to be so high.
Right. Okay.
Okay, are we on to the next one?
Yes, sir.
All right, so this is a slide that's supposed to have the video of the flight motion. Mike will have to play that when we're done, but basically all, I'm going to burst a lot of bubbles here probably. All bullets, when they exit the tube, have small amounts of wobble. And that does not mean the bullets are unstable. Okay? It's the differences in the wobble magnitude and direction that cause a scatter of fall of shot at the target. Okay? The smaller the wobble magnitude, the smaller the groups are going to be. Okay? And so the photograph I have on the right-hand side there, that's a target taken from a handgun at, what was the distance? I think it was only like 10 yards. But it's very obvious that that bullet is not flying at 0 angle of attack. Okay, so it happens on, like I said, I hate to burst people's bubbles, but the wobble happens on virtually every bullet that leaves the tube.
Is there a difference between a flat base bullet and a boat-tailed bullet?
In terms of how much the bullet wobbles?
A wobble, yeah.
Well, okay. So one of the things that controls the magnitude of the wobble is what we would call the Borelay length. So you can think of it as the wheelbase length. It's the distance between where the rifling first touches the bullet and where the rifling last touches the bullet. And the longer that is, the smaller that wobble is going to be, assuming a perfectly made bullet.
Mm-hmm.
Okay. So as the bullet makes the transition from the cartridge case into the rifling, it's going to be slightly tipped with respect to the bore center line. And it's that tilt in bore that is the root cause of the wobble as the bullet exits the tube.
Okay, so a longer shank of the bullet that
Yep.
touches the bore that rides in the
Yep.
bore
And
is
touches
going to have
the tops of the lands. Yes.
tops of the lands is going to be a more accurate bullet. Okay.
You would expect smaller groups from it. Yes.
Okay.
Accuracy is another thing. Accuracy is where is the mean point of impact relative to my aim point.
Right. Which
That's not group size.
right. Yeah.
Okay.
That group size is dispersion.
Right.
Um,
Accuracy.
precision. I think we would call it precision.
Yes.
Okay. That would be a better name for it. Okay.
Yep. Yep.
Okay.
Yep. Questions here? We'll have to go play the video when we're done. We'll have to have a little session where we play the two videos. Okay. So what do long-range target impacts look like? There's perfectly circular, which is what you would expect to see in a normal supersonic strike regime, strike velocity, okay? Not quite circular would be normal at a subsonic strike velocity. The bullet has what we would call a minor dynamic instability. The bullet basically cannot fly at zero angle of attack with respect to its velocity vector. And as a result, you get this elongated hole in the target. Okay. And the last one is a keyhole. And I would tell you, that's not something that you would see under normal flight circumstances. That means the bullet probably has hit something else before it hit the target. Okay.
Okay.
Now, you can also see those short range if you have inadequate twist rate. But here we're presuming we have enough stability to get us past, the first 300 yards of flight. Okay. So if you're seeing a keyhole at very long ranges, what's happened is you've piled into the dirt or you've hit a bird in flight or a branch or something else.
Baffle strike.
Baffle strike, I think you would tend to not get to the target.
Okay.
I was at a test one time at Aberdeen with the services, and when they were shooting at a threat vehicle with a long rod, and we're taking radar data on this thing, and just prior to impact, the trace went hog shit wild. I mean, it just hit a brick wall, We went down to the target and had a look at it, and the rod had piled in sideways. I'm like, that bullet must have hit something. The Marine Corps major started tearing down branches uprange until he found one where we had actually hit it. And And so he bitched at the range people. The next day we came back and they had trimmed all the branches. So basically hitting that branch tore the fins off the projectile, made it unstable, and that caused the problem. But there you are. There you are. And then my last slide here, the factors that are important for long-range shooting. Basically, there are two error categories when you're talking long-range shooting. The first is a random error, and that causes scatter in the fall of shot around a displaced mean point of impact, okay? And the mean point of impact is displaced due to bias errors. So the bias errors you can correct for, okay? It's, an average wind, crosswind, a muzzle velocity shift, that sort of thing. The random errors, you're unfortunately kind of hosed on. There's no get well. You cannot do anything about the random errors because they're random.
Okay. So
when the guys are doing ammunition development, what they're focused on are the random errors. They want to make, through design or through manufacture or a combination thereof, they want to make those random errors as small as possible. The bias errors, that's to some extent up to the shooter. How well can I read the winds? How well can I aim the gun? How consistently can I hold the gun? Those sorts of things. Okay, so it's sometimes useful to put the misses into these two categories.
So a manufacturer making ammunition sits there and says, my random errors are velocity, extreme spread, and standard deviations and all that kind of stuff. Whereas the shooter, we all know what the shooter, the shooter's problems are, especially at longer ranges, because he has to interpret all the conditions that are going on at the time.
Right. So the company that I used to work for, I'm doing a little consulting with, and we're doing a bullet design for an unnamed company, and kind of close in, everybody worries about the random errors. Okay.
Mm-hmm.
And that's, bullet quality, how concentric is the jacket with respect to the interior? How well consolidated is the core with respect to the jacket? Are we using kind of very high consolidation pressures to make sure there aren't any voids in the core material? That kind of thing. Okay.
Mm-hmm.
The bias, once you get out to very long ranges, the big swings are the bias factors.
Right.
How much is the crosswind? That's going to blow me off target. So and you can make the numbers. It's just a matter of, you got to agree on an error budget and then turn the crank and find out how sensitive you are.
There's a whole lot of difference at 1,000 yards with a 3 mile an hour crosswind. That varies from 3 to 5.
Yep.
Than there is at 100 yards.
Right.
You're looking.
You're much more sensitive at 1,000 than you are at 100, obviously.
Right. Okay.
Yep.
All right.
Yeah.
Oh,
And we've got,
discussion.
I do have a slide that talks to some of the Met errors,
Okay.
but we don't have them tonight, so we'll have to put them aside.
Mhm.
I stop sharing and let you share, Mike.
Yeah. Odor Sigurdsson, who's from Iceland. He's been a loyal
Okay.
listener for a long while. So I must have missed this when I was letting the dogs out. So guess best to have 20-inch plus barrel and minimal freebore for
20 inch
accuracy.
20 inch plus barrel is a good idea for most rifles. In terms of free bore, I have not studied that. Okay, let me just say that the best shooting rifle that I own, I have a Ruger precision rifle in 6.5 Creedmoor. That there's the bullet wobble, and that rifle has a very substantial free bore. So I don't think
He's talking about
in terms of
wobbling.
Oh, I the pressures and velocities and loads on the bullet during that initial transition to the rifling are pretty small. So I don't think it matters a whole lot. Okay. Yeah, my 6.5 Creedmoor Ruger precision rifle has got a very substantial free bore in it, and it. I mean, I've shot some really tiny groups with that thing. Like, let me see if I can find it. And I can hold it up to you for you.
I don't think free bore is a real problem. I mean, Weatherby's for a long time had tremendous amount of free bore in them, and they were accurate cartridges.
Right.
Do I want less free bore? Yes. Do I want a certain amount of free bore? Yeah.
Okay, so this is a. Let me see if I can get you up here. This is a 5-shot group at 100 yards with the Ruger precision rifle with hand loads. You know, and pretty happy with that. This is another on the same target 5-shot group with a 6.5 Creedmoor, and the rifle is basically stock, not quite stock. When I first got it, I had an issue with headspace dimension that was set a little too short. I sent it back to Ruger. They reset it to +2. I'm happy, and those groups are the groups that got shot with the +2 setting on headspace. So if you ask me if headspace is a big swing on group size, I would tell you not a big factor. So have we got, Mike, have we got the excuse me, have we got the case hitting the chamber wall?
Let's see here. I don't see that one.
Oh, all right. It was under 5.56, as I recall.
Oh, so it's part of that whole.
It
Because
was MP4, MP4 extension, I
yeah,
think. Oder says he's got an old 308 restricted by the cartridge. Free bore is extremely long. He can't play it around too much. Yeah, so what you see here on the case chamber interaction is so the axial ring location midpoint, and that's inches from the base of the cartridge case. And the radial displacement at 0.4, that's the gap that the case body has to close in order to seal the chamber. And we're stepping through in time here, and 2 milliseconds is the total time of the analysis. And that includes we could call it the blowdown, the emptying of the gun after shot exit. Can you play that again, please, Mike?
Sure.
And I'm going to ask it, can you stop it by any chance?
Yeah.
Okay. Run the go button. Okay, stop. Okay, so where we are here, so up at like 1.85 to just over 2 inches from the barrel, that downward sloping going from left to right, that's the case neck. And between there and 1.7 inches is the shoulder. We don't do a particularly good job of analyzing the shoulder, but basically what's happened is we've contacted the wall at 1.7, and that contact point is running backwards as the pressure increases in the cartridge case. Mash the run button there for me, would you, Mike?
Yep.
And it goes all the way out, and now the case is in contact with the chamber wall. It continues to deflect outward, and then as the pressure comes off, the combined structure comes back, and then you'll see it dip below the 0.004 inch as the pressure in the case continues to blow down. And you can see it, with the exception of perhaps down by 0.9, most of it comes out of contact with the case, with the chamber wall.
And we're back to the beginning.
Yep.
Okay.
Okay, so as the cartridge case grabs the chamber and holds it back,
Yep.
and then it relaxes. That limits the amount of rearward thrust on the bolt.
Yes, there's substantial load shed in friction at the case exterior chamber interior interface.
Okay.
Provided the surfaces are dry, and we're talking about a metal cartridge case.
And a lot of gunsmiths nowadays slightly roughen up the chamber walls. And is that to help the cartridge grab?
I have heard that before. That would surprise me greatly, because kind of what's good for the gun hurts the case and vice versa.
Okay.
Okay, so if you roughen up the chamber, you're increasing the load sharing between the case and the chamber, which reduces the thrust on the bolt. The problem is you're making the case work harder. Okay.
Okay.
And if you make it really polished, very finely, very smooth surface finish, you polish it or whatever, then you got the other problem. Now the gun's taking the brunt of it, and the case is not holding up its end of the bargain.
Okay.
Okay.
I know that my gunsmith runs a light sandpaper in the chamber, just
Okay.
to it doesn't seem to affect the cases. It's not real rough, but it kind of takes the smoothness out that the cutters put into it.
Oh, okay. If we're talking cutter surfaces, yeah, probably
Right.
needs to be polished a little bit. But
Mm-hmm.
I would say that's probably making it smoother. That's me.
Okay.
Okay. And somebody, Truth wants to ask me if Underwood Ammo is a company that I'm working with. I can't say. I can't say.
We understand.
It might be them and it might not be them. I can't say. Okay.
All right. This was a very, very informative show.
Yes, indeed.
Well, thanks very much for having me. If there are some other topics that you'd like me to yak at you about, just let me know.
Yeah, absolutely.
I appreciate just throwing out the Miller formula. Okay.
Yeah, I mean, like I said, if you had nothing else available, yeah, okay, fine, but I wouldn't be betting my life on it. Let's put it that way.
Okay. So that the explanation of the cases, yeah, a tremendous amount of information here that's going to take us a few weeks here to digest.
Well, and if anybody, if anybody has questions and they want to pester me directly, they can go to my website, www.bulletology.com, fill out the contact form, let me know your question.
Now all I got to do is figure out that formula you have and see if I can put it in Excel.
Okay.
All right, sir.
Well, thank you, gentlemen. It's been a pleasure.
No, it's been our pleasure.
And it's way past my bedtime. Being an East Coast guy, it's way past my bedtime. You catch me in another couple of months, and I'll be in Colorado, and I'll be an hour behind you, so that might work better.
Well, we got people from Iceland all the way to Alaska, so we're all over the place.
All right. Well, again, thank you very much, and greatly appreciate it.
We appreciate it. You have a good night, sir.
I will. Bye.
Wow, that was deep. Don't hear you, Mike. You're muted.
I don't know how to do this. What a day. So
3 hours. We did good.
Yeah.
Considering.
Yeah, I mean, just I mean, I told him basically I was just gonna, here we go, and away we go, and however long it takes is however long it takes. So I was
Yeah.
laughing. I was laughing about truth. That's what she said.
Uh,
3 hours. Holy crap! Her uterus fell out.
yeah.
Oh.
Unreal.
Jeff is gone, but I've got to get his book title. Oh, cranky. So I've got a copy of the all the stuff that was shown tonight. His website is bulletology.com. And my dog is gassing me out. Thanks, Allie. And his book is on here somewhere. Ammunition Demystified: The Non-Bubba's Guide to How Ammo Really Works. And it is on Amazon.
Another one to the list.
Mm-hmm.
Boy, at my age, I wonder if I can read it all.
Ooh. So as I typed that in there, and the next book that comes up is U.S. Army Ammunition Data Sheets, a directory of small caliber military cartridges. Remy, what do you want? You were already outside and you came out on your own. Oh, so his book comes on paperback and Kindle.
Oh, okay.
So
Yeah, I just wonder if that formula I can put in Excel and make it work.
I don't know. Crikey. So, well, I think we're going to cut this one pretty short.
Yep.
Make sure you swing by Patriot Patch Company. Check them out. Check out camerado.com. RLP is the code. Or no, FRN is the code for 10% off at Patriot Patch Company. Reload is the code for Camerado. Make sure you're paying attention to what's going on with Second Amendment. Support organizations that are helping to fight for your rights. Kind of be careful of who you're giving money to, because you make sure they're doing good stuff and they're not just out there, grandstanding and throwing things out there to try and get more money and stuff like that. So, Remy, come here, buddy.
I think we're going to do away with the good night and go right to our.
I'm just going to say, make sure if you're struggling, reach out, get some help.
Exactly.
988 or 1-800-273-8255. We want you here. We need you here. Thanks, everybody, and have a great night.
Good night, all.